Hi, distinguished guests, members of NBAS, Ambassador. Thank you for inviting us here today. My name is Gaston Petrocelli, and I'm the Japan country head for Core Power. And we are working on a very different approach to what we have been seeing today so far. We are developing a market for new nuclear in maritime. And before I start, I would really like to encourage you all to be willing to think differently. Nuclear has been beaten up for decades with fear and mistrust, generally encouraged by those who would profit from its downfall. But we believe this is changing, and it is changing fast, and that new nuclear will have a very important role to play in the world of tomorrow. And this is why. So basically, as a global industry, and also as individual citizens, we have two main challenges ahead of us. First, we must produce less waste and emissions to do our part to stop the warming up of the planet, to slow climate change, which is mainly caused by our release of waste and exhaust gases into our natural environment. Second, we must also remain economically competitive. Shipping, as we know, is one of the world's most fiercely competitive markets, which is serving more than 80% of global trade. It is essential that we continue to do that in an economic manner, maintaining the conditions for a competitive market that both innovates and also creates value. As Eric mentioned during his keynote, our energy use and the efficiency of it sits at the very center of that premise. The global push for a fair energy transition and an environmentally sustainable ocean transportation sector will, at the end of the day, come down to what matters, which is energy density and energy efficiency. Simply put, the more fuel we use, the more waste we produce. And conversely, the less fuel we use, the less waste we produce. The waste is different, but still waste. And that's why the energy content matters. Our current low sulfur IFO 380 contains an average of 41 megajoules per kilo, which equates roughly to about 11 megawatt hours of power per ton of fuel consumed. Our industry focus on synthetic fuels made from green hydrogen contain less than half the energy of bunker fuel. Green methanol contains just 20 megajoules per kilo, and green ammonia a little bit less. Our industry transition to this end of the energy spectrum would therefore result in more than 100% increase to our fuel consumption, and with the corresponding increase of waste and the emissions footprint. This is where new nuclear could come in. Nuclear fuel from uranium, which has been safely and efficiently used in power generation and nuclear navies since the 50s, contains 80 million megajoules per kilo. That is the equivalent of 22 million megawatt hours per ton of fuel. For an easy comparison, that's roughly 4 million times more than the green fuel proposed alternatives. Now, the science, the physics tells us that the amount of fuel and the fuel efficiency guide the quantity of waste we produce. Unused carbon in the exhaust from the burning of bunker fuel mixes with oxygen in the air and creates about 3 tons of CO2 per ton of bunkers consumed. That's part of how our industry contributes 2.5% of the 50 billion tons of global CO2 emissions every year. LNG and green methanol could improve a little on this, while in green ammonia, the pilot fuel required is the only source of CO2. With nuclear fuel, since we use so little of it, we produce insignificant quantities of waste. Now, this waste, of course, is toxic and is harmful if you ingest it, but it's never released into the environment, and like we do with exhaust gases, for example. And if it's not delivered or ingested, it is, of course, not harmful. So comparing what we have with what we can have in the future reveals the potential destinies for ocean transportation and whether we can become both environmentally sustainable and also remain economically competitive. With our current bunker fuels, it's difficult to see from there, we continue to emit carbon emissions. We will for sure have to pay carbon taxes. They are coming. We will need to keep speeds low to save costs and emissions, and we depend on the volatility of the price of fuels, which also remain outside of our control. And of course, we will need to switch off their engines when we are in port and rely on local power grid for shore power. With the green fuels option, we will need to store more than twice the amount of fuel on board. That means we would carry less cargo. We would sail at slower speeds in order to save whatever we can. And the costs, scientific and economics estimates show that would be borderline extreme. We would also probably still pay carbon taxes, and the emissions are only reduced. And we would also, of course, continue to do cold ironing in ports. Now, with the new nuclear option, using new marine-appropriate nuclear machines, we could in principle have no fuel tanks, which translates to carrying more cargo instead of less. We could potentially sail at higher speeds because there's no need to conserve energy. And new nuclear reactors could be fueled for the lifetime of the ship, so we could have stable low costs and emit nothing at all. Lastly, as ships could be powered by new nuclear electric systems, we could provide clean electric power to the ports, helping to decarbonize the ports of coal and then change our social contract with the people that live in and that work in those ports. Now, nuclear is not easy. There are substantial challenges ahead in the technology, the integration, the regulation, finance, and of course, public liability. A recent work by an expert group associated with the US Department of Energy, the National Reactor Innovation Center, the group is called the Maritime Nuclear Applications Group. They carried out a research into new nuclear technologies that could function for the marine industry. And they concluded that there are 3 key criteria that must be met for this new generation of nuclear reactors to be accepted in the marine markets. The report is available. If you want to have a copy, please let me know. The first criteria is exceptional fuel efficiency of new nuclear, which could provide a fuel cycle for the lifetime of the vessel. This could remove the need to refuel reactors and the handling of nuclear fuels and nuclear waste in ports. The second criteria is that new nuclear reactors for marine must become affordable, mass-assembled products. And to achieve this, we will need to see quality manufacturing of modular designs, modular construction of the integration systems. And finally, for nuclear electric power ships to call in ports, and also to transit canals and waterways, we will need to see the emergency planning zone, the EPZ, which is required around all reactors, to shrink to within the boundaries of the ship. In order to achieve this, the reactors must be small and unpressurized. With ambient or no pressure in the reactors, there's no radioactivity could physically be dispersed to the environment in case of a leak or a malfunction. Now, the EPZ matters, and it is the main reason why nuclear as we know it today has not been adopted by the shipping industry. It is essentially the difference between unlimited liability of maintaining a large EPZ versus the limited liability of maintaining a small EPZ, which is contained within the boundaries of the vessel. The examples you see here illustrate that point. With a large EPZ, the operator of the vessel would be responsible for the evacuation and cleanup of the area in a port or even a whole port city in case of an accident. With a small contained EPZ, that liability would not extend beyond the railings of the ship and could then be covered by marine insurance. It is a big difference. In waterways, as you can see on the right, where the EPZ is moving together with the vessel, a large EPZ is almost an inconceivable liability burden, even for the largest vessel operators. Again, a small EPZ, not beyond the boundary of the hull, changes all that. Now, development timeline. So new nuclear is being built today and can be with us quicker than you may think. Much of the early research and the development started after the Fukushima Daiichi incident in 2011. Then we realized that we needed to find different and better ways to do nuclear. Financial funding of new designs has been growing substantially since 2020, and we expect to see the first experimental reactors start up in 2025. If successful, and we are confident they will be, that could see marine demonstration by 2028, first commercial deployments at sea in 2030, and a ramping up of serial commercialization and mass production from 2035. Just think of the effect. Every Cape-sized bulk carrier powered by a new nuclear electric system could reduce CO2 and greenhouse gases by 1.5 million tons. Floating new nuclear power plants could generate abundant zero-emission power to produce low-carbon fuels at scale when needed, where needed. Substantial work is being done to facilitate the modernization of safety standards, class rules, and international regulations for nuclear ships. I'm very pleased to tell you that the United Kingdom passed the Merchant Shipping Nuclear Ships Regulation 22 into law last week. Other major nations will follow, which will enable demonstration and generate evidence to be shown to you, to the industry, and to governments around the world that new nuclear for maritime is a key strategic element in the decarbonization of the marine industry. So we must recognize that the only true zero-emission energy source we have is nuclear, and that a little knowledge goes a very long way. I invite you all to come to our first event for new nuclear for maritime we're having in Singapore on the 9th of February 2023. But hurry up, because the demand is high and the places are limited. And with that, thank you very much.